This is Lab 5, Faraday's Law. The purpose of this lab was to apply Faraday's law to a falling magnet in order to calculate the magnetic force on the magnet due to a conductive tube. In part 1, we determined the average time it takes for a bar magnet to fall through a roll of aluminum foil, and we found this to be 1.142 seconds. And then in part 2, we created a computational model in Python to simulate the experiment, and we found the time it takes for the magnet to fall through a stack of rings, and this was equal to 2.182 seconds. And we also calculated the magnetic force exerted on the magnet due to the rings. Some fundamental principles for this lab were Faraday's law, specifically induced current and flux, the PHYS law to calculate magnetic force, and Newton's third law, which stated that the magnetic force on the tube has the same magnitude and acts in the opposite direction of the magnetic force on the bar magnet. And finally, Newton's second law, which we use to update the velocity and the position of the falling magnet. So, for part 1 of the lab procedure, we first determined the north pole of the bar magnet using the magnetometer, and then we recorded the magnet with the north pole on the bottom falling through an aluminum tube. And then we calculated the time it takes the magnet to fall through the length of the tube. We repeated this process 5 times, and then we calculated the average time it takes the magnet to fall through the tube. So here's my data. This is the average time that it took, and then these are the dimensions of the tube. An important thing to note is that a falling magnet would stick to the sides of a ferrous tube. However, a non-ferrous tube is non-magnetic, so its properties won't affect the motion of the bar magnet. For part 2 of the lab procedure, this was the coding part, and so the bar magnet was modeled as a point dipole, and the tube was modeled as a stack of rings. First, we calculated the magnetic field due to the bar magnet. Then we calculated the rate of change in the magnetic flux through each ring. This was done by calculating the flux and taking the derivative with respect to time. Then we found the induced current in each ring using Faraday's law, and this was done by dividing the values found in part 2 by the resistance of the corresponding ring. Then we found the force on each ring due to the magnet using the PHYS law, where delta L was the circumference of the ring and B was the y component of the magnetic field on the ring. Then we summed the forces from part 4 to calculate the force on the magnet using Newton's third law, and then we found the net force on the magnet, and finally we updated the position and the velocity of the magnet using Newton's second law. Here's the first part of my code, and here's the second part. Here is my computational model. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So the slope of the plot is equal to 0 from about 0.3 seconds to 2 seconds, and so the magnitude of the gravitational and magnetic forces are equal during this time interval. Thus, the net force acting on the bar magnet equals 0 during this interval. And so for some simulation questions, first, which color corresponds to clockwise current and which counterclockwise? From Lenz's law, the magnetic field to the magnet is increasing downward, so the flux is increasing downward. The B from the induced current points upwards to oppose this change in flux. Using the right-hand rule, the induced current is counterclockwise, and since the north pole enters the tube first and the simulation shows blue below red in the tube, blue corresponds to counterclockwise and red corresponds to clockwise current. And when you flip the magnet around, the magnet takes the same amount of time to fall through the tube, and the velocity versus time plot is unchanged. Using the same logic from number 1, which is the application of Lenz's law, the induced current is now clockwise. And so the total time in tube for the real-world system we found to be 1.142 seconds, and for the computational model we found it to be 2.182 seconds. And the reason for the large difference is due to my large value of the magnetic dipole moment from Lab 3, and so decreasing this value makes the time for the computational model closer to the real-world time. So, some more questions. What if the resistivity of the conductor were reduced as close as possible to 0? Then the induced current would be larger, and so the magnitude of the upward magnetic force would increase, and so the magnet would fall slower through the tube. And also, if holes or slots were cut into the tube, then the rings wouldn't be fully complete, so there would be an increase in resistance and a decrease in the induced current, and the magnetic force from the rings would decrease so that the magnet would fall faster through the tube. So in conclusion, we observed the motion of a falling magnet falling through a conductive tube physically and computationally. We found the time it takes to the magnet to fall through the length of the tube, and then we also explored several important physics principles, including Faraday's law, induced current, and Newton's second and third laws. And finally, we calculated the magnetic force on the magnet and on the tube. Thank you for watching my video, and I hope you enjoyed it.